Hey everyone, and welcome. Today we're going to tackle one of the most misunderstood topics out there, network performance. We're all chasing faster internet, right? But what does fast actually mean? In this explainer, we're going to pull back the curtain on why your connection might feel slow, and I promise you, the answer isn't always what you think. So let me ask you something, and I bet this sounds familiar. You're paying for that awesome, top-of-the-line gigabit internet plan, you run a speed test, you see this giant number, and you think, yes! And yet, clicking on a website, loading a page, even playing a game can still feel kind of sluggish. What on earth is going on? Yeah, we've all seen this screen, right? That huge number for your download speed. That's your bandwidth. And don't get me wrong, high bandwidth is great, but it's only half the story. The other, and often way more important half, is that little number over on the left for ping, which is just a measure of delay, or what we call latency. And that, my friends, is the hidden culprit. And that is the crucial idea we're digging into. Performance isn't just about how much data you can cram down the pipe all at once. It's all about the delay before that data even starts to move. It's about how fast that very first piece of information gets to you. This is the fundamental difference we need to understand. All right, so let's get right into it. The two pillars of network speed, latency and bandwidth. Once you really get the difference between these two, almost everything about how the web works will just click. Okay, this image is pretty much the perfect way to think about it. Imagine your internet connection is a water pipe. Bandwidth is the width of that pipe, how much water can flow through at the same time. Makes sense, right? But latency is the length of that pipe. It's how long it takes for that first drop of water to travel all the way from one end to the other. See, you could have a massive, super wide pipe, but if it's a mile long, you're still going to wait a while for that first drop to arrive. So to put a fine point on it, latency is just a fancy word for delay. It's the travel time. How long does it take for one single packet of data to get from point A to point B? And we measure it in milliseconds, or thousandths of a second. This is the length of the pipe. And then you've got the other side of that coin, bandwidth. This is all about capacity, or throughput. What's the maximum amount of data you can shove through that pipe over a set period of time? This is the width of the pipe. And you know, this is the number that internet companies love to advertise. But like we're seeing, it's only half the equation.
And believe me, this is not just some abstract techie concept. In the world of high-frequency stock trading, milliseconds are literally millions of dollars. A company spent over $400 million to build a special transatlantic fiber cable just to shave 5 milliseconds, 5/1000ths of a second, off the trip between New York and London. That's $80 million per millisecond. Latency has very real, very high stakes.
Okay, so where is all this delay actually coming from? It's not just one thing, you know. To really get it, we need to follow a single packet of data on its journey across the internet. So every single little packet of data goes through 4 different kinds of delay. First, you've got propagation delay. That's just the time it takes to travel the physical distance. Then there's transmission delay, how long it takes to actually push all the bits of your packet onto the wire. Third is processing delay, where every router along the way has to stop and think for a microsecond about where to send your packet next. And finally, queuing delay. If a router's busy, your packet has to get in line just like a traffic jam. In that last one, queuing delay, oh man, that can become a huge problem. There's this phenomenon called buffer bloat, which is just a fantastic term, and it's a perfect example of this. It happens when our network gear tries to be a little too helpful. So here's what happens, and it's kind of wild. To avoid losing any data, a lot of routers have these gigantic memory buffers. So when traffic gets heavy, instead of just dropping a few packets, which would tell the network, hey, slow down, they just let the line get longer and longer and longer. This creates this massive, invisible traffic jam inside your router, and it leads to these huge, unpredictable spikes in your latency, even when your bandwidth is totally fine. But out of all those sources of delay, there's one that we just can't do anything about. It's not an engineering problem, it's literally a law of physics. And that unbreakable limit? The speed of light. Now, data in fiber optic cables travels incredibly fast, about 2/3 the speed of light in a vacuum, but it's not instant. This table shows you the absolute minimum time it takes for a signal to make a round trip. Think about it. Every single time you click a link, your request has to make a round trip. Just to ask for a web page from a server in Sydney and get the first byte back, you've already burned 160 milliseconds. That is a hard physical limit you can't engineer your way around. So what do these numbers actually mean to us as humans? Well, research shows we start to feel lag at around 100 milliseconds. Anything over 300 and an app or website feels sluggish.
And after a full second of waiting, our brain literally checks out and starts thinking about something else. So when a simple trip to Australia and back can eat up 160 milliseconds of your lag budget, you start to see we don't have a lot of time to waste.
And here's the crazy, ironic part of all this. After your data zips across an entire ocean at nearly the speed of light, it often hits its worst traffic jam in the last few miles, the stretch from your internet provider's office to your actual house. This is what we call the infamous last mile.
There's this cool little command called traceroute that actually lets you see this journey hop by hop. Look at this example. Just getting from the computer to the Wi-Fi router in the same room takes 7 milliseconds. Okay, but the very next hop, just to get to the ISP's equipment down the street, adds another 20 milliseconds. Like, what? Your data hasn't even properly left your neighborhood yet, and you're already at nearly 30 milliseconds of delay.
And as you can see here, this last mile delay really depends on the tech you're using. According to FCC data, fiber is the clear winner, adding about 18 milliseconds on average. Cable adds 26, and old-school DSL can tack on a whopping 44 milliseconds. And remember, this is all delay that happens before your data even gets on the super-fast internet backbone.
Okay, so after all of that, what's the big takeaway? What should we really be focusing on if we want things to feel faster? The key insight is this. It's not about getting more bandwidth, it's about making fewer trips.
Well, it means we have to start building our systems to be a lot smarter about latency. We need to reduce the number of back-and-forth round trips that an app or a browser needs to make. We can use things called content delivery networks, or CDNs, which are basically copies of websites stored on servers all around the globe, physically moving the data closer to you. And we can use smart tricks like caching to store data locally so you don't have to go all the way back to the server every single time.
And that really brings us to the single most important point of this entire explainer. For most of the things we do online, browsing websites, using apps, playing games, latency, not bandwidth, is the true performance bottleneck. Every time you click, you're starting a new trip down that long pipe, and making the pipe wider doesn't make that initial trip any faster.
So I'm going to leave you with this question to chew on. As we continue to build this incredible digital world, what's more important? Should we focus on building wider and wider highways with more and more lanes, or should we get smarter about our digital city planning, finding shorter routes and reducing the distance we have to travel in the first place? It's something to think about the next time you click a link. Thanks for joining me on this explainer.